Welcome to the workshop. We want to continue taking a look at the second section of the appendix, equivalent statements, or logical equivalence, rather. So let's take a look at our next example. So for this example, we actually proceeded with a definition. When we have a compound statement that is true for every possible combination of values of the component statements, such a compound statement is called a tautology. Okay, it's always true. A tautology is always true. And this particular compound statement is a tautology. And we just want to demonstrate that by finding the truth table for it and observing that the entire column associated with the truth values of this are all true, right? All possible values are simply true. This compound statement has a specific name. It's called the modus ponens. That might not be the correct pronunciation. I think that's Latin. Doesn't matter. Anyway, this is used when we are writing proofs. So we may reference back to this in order to understand that a little bit. Although we may explain things a little bit differently than using this idea. But anyway, let's take a look at the truth table for this. Still, the components themselves are only P and Q, so we need to know the value of the component statements, P and Q, or the possible combinations. So let's see, true, true, false, false, true, false, true, false. That's all possible combinations of truth values for two component statements. All right, now we need to build this up. So the first thing that we're going to do is P implies Q. Then we'll take a look at P and P implies Q. And then we can finally get the entire thing. So the first thing is P implies Q. P implies Q is true as long as we don't have P is Q true and Q is false. So true, false, true, false. So true. Gosh, what am I doing here? All right. So again, there's one way that you can, maybe another way that you can think of it, that it's kind of easy to go through the implications. Whenever you have that P is false, the implication is true. When you have the premise, right, the premise is false, the implication is true. When the premise is true, then the implication is true as long as the conclusion is true. So premise true, conclusion true, implication true. Premise true, conclusion false, implication false. Excellent. From there, we can do P and P implies Q. So we are taking a look at the value of this and the value of that. And since it's the conjunction, it's true whenever both are true. So true and true, it's true. True, false, it's false. False, true, it's false. False, true, it's false. All right, so it's a lot of false stuff so far. So let's take a look at this. We've got this thing implies Q. So P and P implies Q. We're taking all of that and we are, that implies Q. So notice that each column, again, is only one connective of previous columns. This is the connective implication, right? A conditional of the previous two. This is the conjunction of two previous columns. This is the implication of two previous columns. Okay, so we want to build this up in very simple steps. All right, so now this implies that. So true, true, we're good there. False, anytime the premise is false, the implication is true. So I don't even need to check the value of Q for these three. I know that it's true. And there we go. we can see here, right? These are all true. So we see that it is a tautology. Yay! It's always true. All right. So on the other side of things, we could have a statement, a compound statement that is false for all combinations of truth values of its component statements. Such compound statements are called contradictions. And we'll use this as well, the idea of a contradiction as well in our proof writing. This particular compound statement we won't use necessarily. All right, so still P and Q, but what we're going to do is we're going to have to find this thing, and we'll have to find this thing and that thing, and then we can find the entire compound statement. So a lot of smaller compound statements in there. So we need the values of P and Q. All right, so P, Q, and true, true, false, false, true, false, true, false. Let's build up this guy first. So not Q would be false, true, true. And then Q implies not Q. All right, so here this would be Q implies not Q, so it's false here, true, false, true. True, yeah, that looks good. Excellent. Next, let's see here. So we've got this side. Now let's do P and Q. Excellent. Here we are. So P and Q, it's only true right here. And then P and Q, no, right? That's the only case in which both are true. So the remaining are false. All right, from here, we can find the last one that we need, P and Q implies not Q. Okay, so we're looking for these two, and we are taking the conjunction. So as long as one of them is false, I can say that overall it's false. So I have a false, 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 false. So it's false, 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 and false. Here we can see the entire column is false, and such a situation is called a contradiction. Excellent. And that's all that we were looking to show for this video. So we've got one more video to take a look at for this section. So I'll see you guys back in the workshop very shortly.